Okay, so this is the midterm review for EGME 441, Engineering Biomechanics for fall semester 2021, midterm 2. Okay, so I checked the poll on Canvas, and it looks like the two topics that won out was a tie. One was spinal biomechanics, and second one was static analysis. Okay. All right, so I think the way I'm going to structure this review video is that I'm going to first go over some of the core concepts with spinal biomechanics. And so that'll take care of some of your conceptual questions, and then for the rest of the time, I'll do some example problems for static analysis. In particular, I think I'm going to rework a couple of the homework problems for you, just so that you can see those. You can kind of see my thought process that I take when I solve these, because I think I've already done all the ones in the lecture, and so I don't want to redo those ones for the review video. And so I'm going to go through the homework ones. Okay, so let's go over spinal biomechanics first. Okay, and so spinal biomechanics has to do with the modes and forces that are placed on your spinal column mostly. Okay, and in particular, we focus a lot on the lower back, just because that's kind of where most injuries tend to happen. Okay. Okay. All right, and so the spine, remember, is really important for a few key reasons. Okay, and so the first reason is that it's one of the major weight-bearing structures in your body. Okay. Okay. And number two, it protects the really important spinal cord. Right. So remember, the spinal cord is the huge nerve that goes from your brain to the rest of your body. And so if you damage that, then that's that's basically going to leave you paralyzed. Okay. All right. And so just like I mentioned, we focus mostly on the lumbar spine, which is the spine at the bottom. Okay. Because that's where most people tend to hurt themselves. Okay. All right. And so that'll be the kind of the focus of our static analysis. Okay. All right. And so I said the next important thing to know about the spine is all the different sections of the spine. Okay. Okay, so remember, we have 5 of them. And so going from the top bottom, we have the top part of the spine is known as your cervical vertebrae. Okay. The second part of the spine is your thoracic vertebrae. Okay. 3 is your lumbar vertebrae. Okay. Remember, your lumbar vertebrae is the part right above, right over your butt. Okay. Right. Then we have the sacrum. Right. And so that's kind of the top part of your pelvis bone. Then finally, we have the coccyx, which is the your tailbone, basically. Okay. Okay. All right. And so out of these vertebrae, usually the parts that are most interesting for at least biomechanics are the cervical vertebrae, because that's basically your neck, okay? And so a lot of injuries can happen at the neck, and also your lumbar vertebrae, which is at the bottom, okay? Okay, let's see. All right, another important concept to know is how your vertebrae are structured, okay? Right, so remember they have a very, I think their direct classification is a unique shape, okay, or a miscellaneous shape. And so there's really no other bone in the body that's shaped like the vertebrae. Okay? And so we have kind of a cylindrical part, basically, okay. And so this is where, this is the part that bears most of the weight of the spine, okay. And it has this kind of appendagey part on the outside. Okay. And so the structure of the vertebrae is kind of just like that, okay? And so this section right here, this is known as the body, okay? And this upper section here, this is the appendage, basically, okay? Right, and the spinal cord passes right through the middle of this appendage, okay? All right. And so, the other part that's important about the vertebrate bones is are the intervertebral discs. Okay. Okay. And so, in between each vertebrae, we have this, this kind of soft, squishy disc known as the discs. Okay. Okay. And so these discs essentially act like a shock absorber for the spine. Okay, so they're because of their kind of structure, they're able to expand and contract very easily depending on the loads that are applied. Okay. Okay. And they help kind of cushion the weights that are being applied. Okay. All right, but the interesting thing about these discs is that they can also be injured. Okay. And usually an injury to his discs involves it being squished so much that it starts to bulge out. Okay. Okay. And when this happens, this is known as a hernia. Okay, which can be very, very painful. Okay. All right. And so that's the vertebrate bones. Okay. Let's talk very briefly about the muscles. Okay. And so there's several muscles that kind of act as part of your core, right? And so whenever you hear an exercise that say works your core, you're essentially working the muscles around your spine. Okay. Okay. But there's one muscle in particular that's of kind of prime interest in the back, and that's the back extensor muscles. Okay, or another name that you'll hear for them is called your spinal erector muscles. Okay. And so these are the muscles in your lower back that are responsible for basically straightening out your back. Okay. And so if we can draw a stick figure, let me just draw them slightly hunched over just to emphasize this. Okay. Right, and so your back extensor muscles are, over here, okay? And they're basically going to produce a moment around the hip joint going that way. Okay. Right, and so by producing a moment on that direction, it's going to cause your back to straighten out. Okay. And so after being applied to this moment, the person might stand up just like that. Okay. Right, so these muscles are almost always active, and so because they're one of the key muscles that help you maintain your balance or balance of the upper extremity. Okay. Okay. But they're because of their kind of really close proximity to the lumbar spine. If you use your spinal erectors too much, it can actually cause some damage to the spine. Okay. Okay. Right, and this large amount of stress on the spine can cause injury. Okay, and so we talked a lot about that when we talked about proper lifting technique, right? And so the proper way to lift a box is to rely as little on your spinal erectors as possible, right? And so the more that you lift with your back, the more risk that you put yourself at for injury. Okay. All right, and so very quickly, let's, we just talked about herniation, but let's also just talk about the other, common back injury, which is just a general name for lower back pain. Okay. All right, and so lower back pain is extremely common, and so most of the population actually experiences it at some point or another in their lives. Okay, and so the number I have for that is about 85%. Okay. And it's one of the most frequent, if not the most frequent and expensive workers' compensation used in the United States. Okay. All right, and so a lot of lower back pain is caused by mechanical stresses that are in your lower back, caused by the back extensor muscles. Okay, and so it can either cause damage to the discs, it can cause damage to the bones, or you might also strain your back extensor muscle as well when you put it under such strong stresses. Okay. Right. And so if you want to avoid lower back pain, it's really important to use proper work techniques for all of your all your lifting actions or just actions in general. But also just to make sure that you're taking care of it in other ways too. So making sure your posture is straight, and everything like that. Okay. Okay. And so with that, let's go ahead and let's start working on some static analysis. Okay. Right. And so this is obviously going to be a big part of the exam because a lot of the problem solving questions are going to be these types of problems. All right, so we'll try to get through as many as we can right now. Okay, and so first let's start with the let's actually start with the first problem of homework 5, just because you guys don't have the solutions for that yet. Okay. Okay, and so it's going to be homework 5, problem 2A. Okay. All right, and so in this problem, we have someone that's standing on one foot. Okay. And so the free body diagram for this looks like the following. Okay. And so let's say that we have this length right here is L1. This length right here is L2. Okay. This length right here is LM. Okay. Right. We have a normal force that's coming from the ground. Okay. And we also have the weight of the leg that's acting as well. Okay. All right. And so in addition to that, we have a muscle force, and someone go ahead and draw that in. Okay. Right. And then we have all the lengths that are shown. Okay. And then finally, we have the angles. Okay. And so the angle that the leg makes with the ground. Okay. So this angle right here is, we'll call this angle theta. Okay, because it's the angle of the entire leg. Okay. In addition to that, we have two angles right here. Okay. And so we have theta m, which is the attachment angle for our muscle force Fm. Okay. And we also have theta h here. Okay. Theta h is the angle at which the line towards the hip joint, that's the angle it makes with the horizontal. Okay. All right, and the joint that we're summing everything around is this one that I'm circling in orange. Okay, and so this is our hip joint. All right. And so, with all that in mind, let's take this and let's compute. Right, let's compute our muscle forces. And joint reaction forces. All right. Oh, it would help if we had actually numbers for this, right? So let's say L1 is equal to 40 centimeters. L2 is equal to 42 centimeters. Okay. We'll say theta is equal to 75 degrees. Okay. Theta h is equal to 30 degrees. We'll say the attachment angle for the muscle force is going to be 33 degrees. And then LM here is 6 centimeters. Okay. Right. Oh, we have FN as well. FN is 600 newtons. Okay. And then the weight of the leg, as shown, is 75 newtons. All right. And so that's all the parameters in the problem. Okay. And so we can now go and start to solve this. Okay. And so first, just like we always do, let's go ahead and solve the muscle force by summing the moments around the hip joint. Okay. All right. So let's go ahead and do that on the next page. All right. And so, another thing before I forget, and so I didn't explicitly say it in this problem, but you can see that this is a lower extremity type of problem. Okay. And so on the exam, I would actually recommend that you don't, when you come across the statics problems, don't bother asking yourself, like, is this an upper extremity problem? Is this a lower extremity? Is this a spinal problem? And so it'll be better if you just kind of just know the method, and so know how to do a static analysis, because that method can be applied to, you know, anything in this unit. Okay. All right. And so first thing we're going to do is we're going to sum the moments around the joint. Okay. Right. And so you know, along the way, you know, when you're doing these types of problems, it really helps to just do a little bit of accounting along the way, just to make sure that you get every single term that you need to. Okay. All right. And so for the moments, you know, we're going to have one term in the moments for each force that we have in the problem. Okay. All right. And so in this case, we have three forces. Okay. And so first we have the muscle force. Okay. Right. And for now, I'm just going to, you know, normally for the moments, you multiply a force multiplied by its moment arm, but let's just leave this kind of vague for now. And so we'll call this moment arm A. Okay. Right. And so that's the first moment arm for our parameter here. Okay. All right. And so that's going to try, actually, that'll be a negative. Okay. Because remember, the sign convention that we use is that positive moments are going to be, you know, counterclockwise, and negative moments are going to be clockwise. And so since this FM is going to basically try to rotate clockwise around the joint, okay, so we have this FM this way, okay, and so if we draw a complete circle with it, we can see that it's going clockwise. Okay. All right, and so next we have the term for the weight of the leg. Okay. And here's where it gets a little bit tricky, because I think, you know, this is kind of where people start to get confused. Okay. And so I think the primary confusion is, you know, should we use a positive number for this, or should we use a negative number on this? Okay. Because it really depends on what side the weight force acts on the hip joint. Okay. And so if I draw a figure right here, okay, and so let's say that this dot is the hip joint. Okay. We know the weight of the leg is going to be a vertical force. Okay. And so there's no question on that. Okay. But whether the sign that we choose for this is positive or negative depends on which direction this force is acting on relative to the joint. Okay. All right. And so if we have one configuration here where, you know, the resultant force ends up being on the right of the joint. Okay. And so in these situations, you know, if we kind of trace this around, we can also see that this is going to be a clockwise behavior. Okay. And so because it's clockwise, we have a negative here. Okay. All right. But, you know, if the force was on this side of the hip joint, excuse me, on the left side, okay, then maybe our weight of the leg would be something like that. Okay, and so if I trace this around, right, you can see that we're going in the counterclockwise direction. Okay, and so in that case, it's going to be a positive moment. Okay, but for this particular case, you know, we're actually going to have a negative moment. Okay, and I'll show you why in a second. Okay? And in fact, you know, I'll show you a way to kind of set this up so that you're always guaranteed to get the right sign for this. Okay. All right. Okay, so there's our hip joint again. Right, no biggie. You know that this line right here is L1. Okay. Oh, excuse me. Didn't sleep well last night, right? Okay, and so that's L1. And then our weight force is going to be acting at the bottom of this. Okay. Right. And in addition to this, we have this length right here, which is LM. All right. And so the way I kind of see this, and so the way that I think works best for these is to see all the triangles. Okay. Because remember, we have an angle here, and so this angle is theta, okay? Whereas this angle right here is theta h, okay? All right. And so, because this force is vertical right here, okay, for a completely vertical force that doesn't pass through the joint, the moment arm is going to be a horizontal distance. Okay, because remember what the moment arm represents. Okay. And so the moment arm is the shortest possible distance between the force vector and the accompanying pivot. Okay. Okay. And so for a vertical force like this, let's go ahead and extend this force upwards. Okay. And so I'm just adding something to the tail, and so nothing mathematically is changing. Okay. And so if we take the shortest distance between this line and this point right here, okay, which is the hip joint, then we notice the shortest distance is going to be when this line is perpendicular to the vector. Okay. All right. And so if just as an example, let's say that we try to take a moment using this length right here. Okay. And so this isn't going to work because this distance is not the shortest one possible. Okay. But what will work in this situation is if you draw the force vector just like that. Okay. So it's again a horizontal distance that acts horizontal distance between our force vector and the accompanying joint. Okay. All right. And so back to the problem. And so the problem, in this problem, we want to find the moment arm for WL. Okay, so actually, let me go ahead and write that into the equation. Okay, let me just keep this plus down just for now too. Okay. All right. Okay. And so, if this is going to be the moment arm for the weight of the leg, then we're just going to do moment arm B. Okay. Okay. And then we're gonna have the same thing for the normal force too. Okay. And so we're going to do a plus Fn times moment arm okay, and this is going to be moment arm C. Okay. All right. And so let's go about and computing those moment arms. Okay. And so I think this is going to be a process that kind of trips people up. Okay. And so let me start with the well, I guess let's start first of all with Fm. Okay, because this one's pretty easy. Okay. And so for Fm, we're going to look at the Fm vector, and we see that it's attaching at an angle of theta m. Okay. And so the moment arm, or the component, that we're going to take, that's that's going to produce a moment, is going to be minus Fm times Lm theta sine of theta m. Okay, and so that value right there, that's going to go in, moment arm A. Okay, and so I'm not going to draw this again, because this is something that we've seen, so many times in this class. Okay, but let's do the moment arm for element for WL. Okay, and so let me go ahead and draw just one more picture here. Okay. Okay. And so in this picture right here, we have L1. Okay. This distance is Lm. This distance is theta h. And this distance is theta. Okay. All right. And so what we want, because if the WL is acting on this part of the leg right here, okay, we want to know what the horizontal distance is between here and the joint. Okay. All right, and so we can't do this all in one go. Okay, and so we need to do this with a couple calculations. Okay. And so using the curvatures or using the geometries that you're given in the problem, my advice is always to see if you can draw some triangles here, specifically some right triangles. Okay. Right. And so for the for the distance between F1 and the point of attachment, we have this length right here, right? And so we have L1. Oops. Okay. Actually, let me move L1 to the other side. Okay, and so L1 is the hypotenuse of this triangle right here. Okay, since we have the angle theta, let's go ahead and form a right triangle. Okay, right, and so from this right triangle, what we can find is we can find this horizontal distance, right? And so this horizontal distance is going to be L1 cosine of theta. Okay. So this is good because at the end of the day we want as many horizontal distances as possible. Okay. But this is not the true moment arm yet, because that's the distance between the line of action of the force and the attachment location of the muscle. Okay. And so we're not quite at the joint yet. Okay. And so in order to get to the joint, we have to analyze this triangle right here too. Okay. And so if we draw this triangle, okay, maybe it looks something like this. This length right here is Lm. Okay. And this angle right here is theta h. Okay. And so once again, what we're able to find is a little bit of trigonometry will get us these horizontal distances that we need. Okay. All right. And so this distance right here would be Lm cosine theta theta h. Okay. All right, and so now that we have these quantities for us, okay, we need to know what to do with them, because one of them is the distance between the line of action and the attachment point, and the other one is the distance between the attachment point and the actual joint. Okay, and so if we want to get the distance, the horizontal distance between the force and the joint, what we can do is we can just simply take the difference between these two. Okay. Okay, and so that's what we'll do on the next page, and then we'll do the exact same thing for Fn as well. Okay. Okay. All right. So if we take their distance or take their difference, and so we have L1. Let me switch to black again. Okay, and so we have L1 cosine theta. Okay. minus Lm cosine theta, cosine theta h, excuse me. Okay. And so this one, all of these numbers that we know, and so if we can plug these in, then what we get is 5.16 centimeters. Okay. Right, and so this 5.16 centimeters, this is the moment arm for the normal force. Or not, sorry, not the moment force. The weight of the leg. Oh man, I need to get sleep. Okay, and so by that same token, we can use the same logic to find the moment arm for the normal force. Okay, except for the normal force, you know, we have the full leg that we're taking into account. Okay. And so this entire distance right here is L1 plus L2. Okay. And we still have the same angle right here, theta. Okay. And so the moment arm for the normal force is going to be the sum L1 plus L2 okay. L1 plus L2. Just like we did up here, we're going to have a cosine theta. Okay. And we're going to subtract the distance from the muscle attachment to the hip joint. And so that's going to be another Lm cosine theta h. Okay. And we plug these in, and what we get is 16.03 centimeters. All right. And so now that we have these moment arms, you know, combined with the moment arm that we got from the previous page, we can plug all of these things in and solve for Fn, because the entire moment equation should sum up to 0. Okay. Okay. And so if we plug all those in, okay. Okay. So let me write down one step right before the solution. Okay. And so we have Fn multiplied by 0.1603 meters, okay, minus FL 0.0516, okay, divided by Lm sine of theta m. Okay, and so we plug those numbers in, and what we get is Fm is equal to 2,824.81 newtons. Okay, and so that's the moment, or that's the muscle force that's acting in this situation. Okay, and so now that we have the muscle force, we can then plug those in to find the joint reaction forces. And for here, you know, it's a fairly straightforward process. Okay. All right. And so first, let's start with the reaction force in the x direction. Okay. And again, you know, unless the instructions say otherwise, you can assume that all joint reaction forces are in classical x direction and classical y direction. Okay. All right. And so if we sum up the forces in the x direction, what we get is Fm okay. We're going to get the we're going to need the angle that the muscle force makes with the horizontal, and so that's going to be cosine of theta m plus theta h. Okay. Right. And just because I know the joint reaction force is going to be pointing to the left, because, you know, Fm is the only one going to the right, and so I'm going to put a negative jx there. Okay. And so we plug in for Fm that we just solved for, and we get Jx is equal to 1282.44 newtons. Okay. And we sum the forces in the y direction. Okay. We're going to have negative jy plus fm sine of theta m plus theta h. Okay. Minus fl, or the weight of the leg, plus fn. Okay. You sum those up is equal to 0. And what we get is jy. Jy is equal to 3,041.92 newtons. Okay. All right, and so that's kind of the full solution to problem 2A in homework 5. Okay, and so the key points that I would say are to use your trigonometry and draw out triangles like this. Okay, and so I know it seems silly to draw triangles like this, but I think when you draw out the triangles, with the appropriate angles, then I think it makes it easy to find the components that you need. Okay. And another thing to remember is that your the components or the moment arms is always going to be the shortest distance between the the line of action of the force and the joint. Okay. All right. And so there's that one. Okay. And so let me do one for the upper trim, just so that we have a little bit of balance here. Okay. And so I think a good one to do for this one is going to be 2C on homework 4. Okay. All right, and so in this one we have a weightlifter here working on doing a shoulder lift, okay, or overhead press. My apologies. Okay, and so we have a an arm that's pointed upwards like that. Okay. And then in the arm, we have a weight, okay, W. And of course, that's going to be directed downwards, just like that. Okay. The lengths in this problem are given as such. And so we have L2 for this one. Okay. This one is L1. Okay. The angles that we have here, let me use yellow for this. Okay. We have this angle right here with respect to the horizontal is theta 2. Okay. And we have this angle with respect to the horizontal is theta 1. Okay. And then additionally to this, we have a muscle force, particularly the shoulder muscle, which is acting in this direction. All right. And so let's go ahead and put some numbers on this one. Okay. Okay. And so some of the parameter values that we have are, we have theta 1 is equal to 50 degrees. Okay. Theta 2 is equal to 60 degrees. Okay. Theta m is equal to 25 degrees. Okay. W1 is equal to 40 newtons. W2 is equal to 30 newtons. And W, the weight in the hands, this is going to be 200 newtons. Okay. And the various lengths that we have is we have L1 is equal to 28 centimeters. Okay. L2 is going to be equal to 33 centimeters. Okay. And LM, I forgot to put it in here, but that's LM. Okay. LM is the usual 6 centimeters. Okay. All right, and so we're going to compute the muscle forces, the deltoid muscle force and the joint reaction forces. Okay. All right, so let's start with the muscle force first, okay? And so just like all the muscle forces, we're going to, sum up the moments around the joint, okay? Oh, I'm sorry, I forgot to put in the weight of the arms. And so we have the weight of the upper arm, and so this will be W1, okay? And then we have the weight of the lower arm, and so this one will be W2, okay? Okay. All right. And so that's the, that's all the forces, okay? And so let's go ahead and sum up the moments, okay? So we do some of the moments around the joint, okay? And so let's go ahead and start plugging all these in, okay? And so we don't have to do anything too special here. The only thing is that, for the weight of the arms and for the weight of the weight, we have to be careful how we choose the moment. Okay, but let's start simple first. Okay, so let's start with the no moment from the muscle force. Okay, and so the muscle force is going to be in FM, LM, okay, sine theta M. Okay, and so that's like usual. Okay, next we have W1 right here. Okay, and so just like we did before, I'm going to draw a triangle. Okay, and so from that triangle right there, we can see that the component that we want is this horizontal length. Okay, right, and the length of that horizontal segment there is going to be the hypotenuse. Where remember the hypotenuse is only halfway up the arm, and so this is going to be L1 divided by 2. Okay, L1 divided by 2. L1 divided by 2 multiplied by cosine of theta 1. All right, and so let's go ahead and input this into our equations, okay? So we have a, this is going to be clockwise. So we have a minus W1 times L1 divided by 2 times cosine of theta 1, okay? All right. And so the next contribution that we're going to have is W2, okay? And so let me go ahead and expand this triangle right here, okay? And so this part's tricky. And so, you have to make sure that, you consider both of these triangles individually, okay? Okay. Right. And so the key here is not to combine them all into one, because what we want in the end is just the total horizontal distance between W2 and the shoulder joint. Okay. All right. And so if we break it up into these two triangles, it becomes a little bit more clear, right? Because first of all, what we need is the horizontal length from L1. Okay. And so this entire length right here, okay, that's going to be L1 cosine of theta 1. Okay. And then we're also going to have this horizontal length right here, which is going to be L2 divided by 2 cosine of theta 2. Okay. Right. And we need to sum these together in order to get the total moment arm for W2. Okay. All right. And so if we sum them together, we get a minus W2, okay, multiplied by L1 cosine theta 1 plus L2 divided by 2 cosine theta 2. Okay. All right. And then finally, we have the contribution from W. Okay. And so the moment arm for W is going to look very similar, right? The only difference is that instead of L2 divided by 2 here, we're just going to have L2. Okay. And so we have a minus W times L1 cosine theta 1 plus L2 cosine theta 2. Okay. And all this is going to be equal to 0. Okay. All right. So you can see, there's quite a bit of work here. just because we had so many contributions from the forces. But but if you take it kind of step by step, it's not so bad. Okay. All right, and so let's go ahead and sum these up and then solve for FM. Okay. And so if we do this symbolically first, then what we get is FM is equal to W1 times L1 divided by 2, okay, times cosine theta 1 plus W2 times its moment arm, which is L1 cosine theta 1 plus L2 divided by 2 cosine theta 2, okay, plus, and this is also in the numerator, okay, so this is going to be plus W L1 cosine theta 1 plus L2 cosine theta 2, okay, and all this is going to be divided by Lm sine theta m, okay, and so we plug in all the numbers for this and we get Fm is equal to 3,173.48 newtons. Okay. And so again, it's something that you just have to take kind of just step by step. Okay. And so, just make sure you stay organized. Okay. And so, take your diagram here and draw it, right? Because it helps a lot. It helps a lot to kind of, keep track of all the forces that are acting. And it helps to keep track of, what are the distances that you need in order to, in order to compute the moment arms. Okay. All right, and so with that, we are almost done with the problem. And so the only thing that we have left to do is to sum the forces in the X and Y directions to get the reaction forces. Okay. Okay. All right, so we have a sum of the forces in the X direction. Okay. This is equal to Jx minus Fm. Okay. The angle that we're going to pick here is actually a difference in between the two angles, right? And so we're going to have difference of theta 1 minus theta m. Okay. Because remember, theta m is defined relative to arm 1. Okay. And so I'm going to go ahead and draw that out on the next page just so you see. Okay. But if we solve for Jx really quickly here, okay, you get Jx is equal to 2,876.15 newtons. All right. And so how do we get, this difference right here, theta 1 minus theta m? Okay, so let's go ahead and draw that out just so we can see it. Okay. And I'll draw it slightly exaggerated just to make it a little bit easier. Okay. Right, and so we have theta 1 on this side right here, okay? And then we have Fm, and so I'm going to draw it a little bit higher up here just so it's easier to see. Okay. And this angle right here is going to be theta m, okay? All right. And so the reason we have the difference in the angle here, has to do with, how we compute these, okay? All right. And so, remember, one thing that I like to do with this is to kind of, think about, plug in some numbers here and see if they make sense. Okay. All right. And so first thing we'll compute here is let's say that we have both angles here equal to 45 degrees. Okay. Okay. And so, this one is going to be located up like that. Okay. So this is going to be 45 degrees. Okay. And then FM is going to be angled like this as well. Okay. So this is going to be 45 degrees as well. Okay. Okay. Right. And so you can see, because of the orientation of these two vectors here, okay, if you have 45, 45, right, you have one that comes up 45, and then another that rotates 45 off of that. Okay, we basically make a letter Z, right? And so we have, a letter Z that's right here. Okay. Right. And so if that's the case, when both of these numbers are the same, we end up with something that's horizontal. And a horizontal angle right here is basically any theta that's like either 0 or 180 or 360, but usually it's just 0 or 180. Okay. Because, when I was first working out this problem, I asked myself whether I should do theta 1 plus theta m, or theta 1 minus theta m, or theta m minus theta 1, or stuff, everything like that. Okay. If we did theta 1 plus theta m, right? If that was the angle for our cosine term here, okay, we would get something completely wrong, right? Because if we had, theta 1 plus theta m, in the case of, if they're equal and they're equal to 45, then this would equal 90 degrees, right? Right. And so what that basically is saying is that, this, this angle right here is angled vertically upwards, which is completely wrong, obviously, right? And so, we have the horizontal, we have it being horizontal, okay? And so with that being said, one correct way that you can do this is simply just do theta 1 minus theta, okay? And so that's going to give us the right answer for that. Because if we do, 45 minus 45, then we end up with an overall theta of 0, right? So 45 minus 45 is cancel out, okay? And so that gives us a horizontal theta, which is what we wanted in the first place. Okay. And so that's how I settled up with theta 1 plus theta 1 minus theta. Okay. All right. And so one last thing we'll do before we wrap up the problem is we're going to sum up the forces in the y direction. Okay. And so in addition to the muscle force and the joint reaction forces, we have the we have all the weights acting in this direction as well. Okay. And so we have some of the forces in the y direction. Okay, this is equal to jy minus fm sine of theta minus theta m. Okay, minus w1 minus w2 minus w. Okay, and all that's going to be equal to 0. Okay. All right, and so if we solve this puppy for jy, and it's the only unknown in this equation, okay, we get jy is equal to 1611.17 newtons. All right, and so there is our jy. Okay. All right, and so hopefully, working out those two problems was helpful for you in this review session, because we've definitely done all the ones in the lectures, but we haven't worked out the homework ones together either. Okay, and so when you're studying for the exam, I highly recommend that you go through problems like this. Okay, because with these kinds of things, practice makes perfect, and so the more you practice these problems, the more you kind of get into that good mindset of what am I supposed to do in these kinds of problems. Okay. And just like I tell everyone for these kinds of problems, that the best way to study problems like these is to not look at the answers, right? And so if you're studying for these types of problems and you're looking at the problem and you're looking at the answer right away, you're not really giving yourself practice, because what can happen sometimes is that you can look at the answer and you say that, oh yeah, of course I knew how to do that, right? But you're not really putting your brain through the practice of starting these problems from scratch, okay? And so, you really have to get that practice, because that's what you're going to do on the exam. And so on the exam, you're going to be given a problem, and obviously I'm not going to give you the answer, right? It's going to be just a blank problem, and you have to go through that, thought process of, doing this problem from scratch, okay? And so definitely make sure you're doing that. And so, of course, you can do this for the homework problems, or you can do them for the lecture problems as well. Okay, and so we worked out a lot of example problems in the lecture, And so definitely use those to your advantage, as you're studying. Okay. Maybe use some just to kind of see what the process is like, but then do some practice, without looking at the solutions as well. And I think, if you do that, you study the concepts on the study guide really well, I think you're going to be in great shape for the exam. Okay. All right. And so that's all we got time for the review session. And so, I hope that was useful for you. As always, if you have any questions on anything, you can feel free to reach out to me, and I'll try to get back to you as soon as I can. Right. And so best of luck studying, and I'll see you next week.